Imagine a mind so powerful it could reshape our understanding of the universe, one that could see beyond the boundaries of accepted knowledge and dare to ask questions no one else would. Throughout history, only a handful of thinkers have managed to challenge the very fabric of reality itself. Albert Einstein, the genius behind E+mc2, and the revolutionary idea that gravity is the curvature of space-time, was one such mind. His theories transformed physics, turning the universe into a place governed by elegant, predictable laws. Yet, even titans can be challenged. No matter how brilliant, no idea is immune to scrutiny or doubt. One experiment would shake the very foundations of his beliefs, sending shockwaves through the scientific community and forcing everyone to reconsider what they thought they knew. The double-slit experiment, a deceptively simple setup with just two tiny slits, would force science to confront the true nature of reality. What seemed like a straightforward test would reveal mysteries that defied common sense. This was more than physics. It was a battle of worldviews, a clash between certainty and uncertainty, order and chaos. On one side stood Einstein, champion of a predictable universe, convinced that nature followed strict, unbreakable rules. On the other, Niels Bohr, architect of quantum theory, who embraced the strange, unpredictable world of quantum mechanics and the idea that uncertainty is fundamental. Their debate wasn't just technical, it was philosophical. Questioning whether reality is truly random or governed by hidden rules, it was a struggle to define the very nature of existence. The answer would come decades later as new experiments and advanced technology put their ideas to the ultimate test, pushing the boundaries of what we could observe and measure. In science, no authority is too great to be questioned. Every breakthrough begins with a challenge, and every revolution starts with a single, daring question. Before Einstein, Thomas Young challenged Newton's view that light was made of particles. At the turn of the 19th century, Newton's particle theory dominated science, but Young was convinced there was more to the story. He believed that light might behave like a wave, much like sound or water. Young's double-slit experiment sent a beam of light through two narrow slits, projecting a mysterious pattern of bright and dark stripes on a screen behind them. This simple setup would become one of the most famous experiments in physics. If light were truly made of tiny particles, as Newton thought, you would expect to see just two bright bands on the screen, each one lining up with a slit. Instead, the experiment revealed a striking interference pattern, multiple bands of light and dark, showing that light was behaving as a wave, not as a stream of particles. Like ripples from two pebbles dropped into a pond, the waves of light overlapped, sometimes reinforcing each other to make bright stripes, and sometimes canceling each other out to make dark ones. This was clear evidence of wave interference. Young's experiment was a turning point. It proved that light behaves as a wave, revolutionizing physics and paving the way for James Clerk Maxwell's theory of electromagnetism, which unified electricity, magnetism, and light. For nearly a century, the wave theory of light reigned supreme. It explained the colors of rainbows, the bending of light through lenses, and countless other natural phenomena that had puzzled scientists for generations. But science never stands still. As the 20th century dawned, new experiments and discoveries began to challenge the wave theory, hinting that the true nature of light was even more mysterious. Einstein's groundbreaking work on the photoelectric effect would resurrect the idea of light as particles, tiny packets of energy called photons, shaking the foundations of physics once again. The double-slit experiment was about to become even stranger, as scientists began to test it with electrons and other particles, revealing the bizarre world of quantum mechanics. The comfortable world of classical physics was about to be shattered, opening the door to a new era of scientific discovery and wonder. In 1905, Albert Einstein revolutionized physics by explaining the photoelectric effect. He proposed that light, previously thought to be only a wave, actually comes in discrete packets called photons, revealing its particle-like nature. This bold idea challenged the classical view and set the stage for a new era in science. This concept of wave-particle duality became a cornerstone of quantum mechanics, suggesting that light and matter can behave as both waves and particles. Yet Einstein was deeply troubled by the apparent randomness and unpredictability at the heart of quantum theory. To probe these mysteries, Einstein devised a famous thought experiment involving the double-slit setup. He wondered, If you could somehow measure which slit a particle passed through, would the mysterious interference pattern, evidence of wave behavior, vanish? Einstein imagined a clever device, a movable slit plate that would recoil ever so slightly when a particle passed through, revealing its path without, he hoped, disturbing the experiment. He argued that, in principle, you could know the particle's path and still observe the interference pattern, directly challenging the uncertainty principle that lies at the heart of quantum mechanics. Niels Bohr, Einstein's great rival in these debates, responded with a profound insight. Bohr explained that to measure the slit's position with high precision, you inevitably introduce uncertainty in its momentum, which in turn blurs or even destroys the interference pattern. In other words, the very act of measurement unavoidably disturbs the system, causing the delicate wave behavior to collapse and disappear. This debate between Einstein and Bohr struck at the very heart of quantum reality. Is the universe fundamentally uncertain, as quantum mechanics suggests, or is it simply that our knowledge is incomplete? Ultimately, resolving these questions would require more than clever thought experiments. Only real-world tests and experiments could reveal the true nature of reality at the quantum level. For decades, the Einstein-Bohr debate was theoretical, until technology caught up. In the 21st century, MIT physicist David Pritchard and his team recreated Einstein's challenge in the lab. They sent individual sodium atoms through a double-slit grating, using a laser to gently detect which path each atom took. By tuning the laser's intensity, they could control how much which-way information they gathered. The experiment tested whether it was possible to know the path without destroying the interference pattern. Einstein's view, a gentle measurement might reveal the path and preserve the pattern. Bohr's view, any measurement would reduce the interference, no matter how subtle. The stage was set for a definitive answer. Nature would decide. The MIT experiment delivered a clear verdict. Bohr was right. As the laser's intensity increased, the interference pattern faded. When the path was known with certainty, the pattern vanished. The uncertainty principle was confirmed. You can't observe both wave and particle behavior at the same time. Measurement doesn't just reveal reality, it shapes it. At the quantum level, particles don't have definite properties until measured. Wave-particle duality isn't just a metaphor, it's a fundamental truth. The nature of a quantum entity depends on the experiment you perform. The observer and the observed are inseparable in the quantum world. This experiment reinforced the measurement problem. Observation is an active part of quantum reality. Bohr's vision of quantum uncertainty triumphed. Was Einstein wrong? In this debate, yes, but that's not the whole story. His challenges forced deeper thinking and better experiments, driving science forward. Great science isn't about always being right, it's about asking the right questions. Einstein's skepticism inspired generations to probe the mysteries of reality. His legacy is richer for his willingness to question, even when uncomfortable. The double-slit experiment reminds us, science is a journey, not a destination. The universe is stranger and more wonderful than we imagine, and there's always more to discover. Stay curious. The next great revolution could begin with your question.